I'm just going to follow the notes that Professor Dupuy gave me. I guess he has talked to you about sets, and what sets are, and the way we usually form of example, the way we usually write down the definition of a set, saying something like set S is all of the elements x such that something is true, some proposition about x is true. And that's usually a good way to write down a set. Or if it's a very small set, you can just write out the elements, or if it has some nice arithmetic progression, there's some other way that we can write it sometimes, but this is sort of the standard way. So example, let A be the set of elements in the integers such that there exists a k that's also an integer, and n is 4 times k plus 1. So we say it's all elements n such that this statement about n is true, and then b, let this be all of the integers such that n is odd. Okay. Those are two different set definitions. And as you might notice, we could also write this one in the same way as that one, but with a 2 instead of a 4, right? Because every odd number can be written as 2 times some integer plus 1. Okay, so we want to prove we will prove 1 that A is in B, and 2 that B is not in A. Right. So what does this subset? Well, this is the symbol means that A is a subset of B, right? So we would write, in general, we write A is a subset of B. What does that mean by definition? It means that A is entirely inside of B, right? So if we want to prove that, then what we really want to prove is that every element of A is also in B. So in other words, we want to prove that if this means that if some element x is in A, then that implies that x is also in B. Right? So if we want to prove that this is true, then this is what we need to prove. We need to prove that if some element is in A, it must also be in B. And if some set is not a subset of some other set, then what does that mean? Well, it means that there's some element in B that's not in A, because then it wouldn't be a subset. Right? So in order to prove that, we don't have to prove something that's true for all of the elements of B. We just need a single example. Right? So it's important to know the difference when you need to prove something for an entire set and when you just need to give an example, and that's enough proof. Right? For example, here, just giving an example of some element that's in A and also in B doesn't really tell us that much. Right? It doesn't really prove anything. But here, we just need to prove that there exists some x in B such that x is not in A. So those are the things that we need to do to prove these things. So actually, maybe I'll erase this and then we'll actually do it for this specific example. So in this case, what do we have? If we have some, let's call it little a, we have some A in A, then by the definition of A of the set A, we have that A is equal to 4 times k plus 1 for some integer k. And then by definition, if some element B is in B, then B is odd, but as I said, we can also write that as saying that B is equal to 2k plus 1. Let's call this k prime just to distinguish it from the previous k. K prime for some integer k prime. Right, this is just going back to the definitions. Right, so now if we have some now we can just say, okay, well, if we have some A and A, then we can just say let my k prime be 2 times k. Right? I'm allowed to do that because that would still be. I mean, if k is an integer, then 2 times k is also an integer. So then we have that A is 2 times 2 times 2k is 2 times k plus 1. Plus 1 is 2 times k prime plus 1 for some integer k prime. But of course now it fits the definition of elements that are in B, right? So then A is in B, which concludes our proof. Because we set this for general A, right? This was true for any. It's true for any A and for any little element A in the set A, right? So then we're done. So this was number one over there. And all of these examples that we do they're kind of very easy, right? And you feel like you can almost just see it just by looking at the sets, right? You can sort of like tell immediately that these will be odd numbers, right? Because this is definitely going to be an even number, and plus 1 it should be an odd number. So that should be true. But it's important to practice doing it very rigorously, because once it gets a little bit harder, it becomes harder to just see whether something is true or not. And it's easier to practice being rigorous on easy things, because then it's easier to see when you make a mistake or when you say something that's not true. But in some ways, sometimes it's hard. If something seems very obviously true, it's almost hard to try to prove it rigorously. So now the other ones, to prove that B is not a subset of A. Proof that B is not a subset of A, all we needed was a counterexample. Right, so what's a counterexample of something that's in B but not in A? Three, sure. So we have that 3. 3 is 2 times 1 plus 1. So 3 is in B, but there's no integer k there's no integer k such that 3 is 2 times k plus 1, because from our basic algebra we know that the only solution to this is when k is a half, which is not an integer. Right? So there's no integer solution to that. So then we're done. So 3 is not in A, and therefore B is not a subset of A. Right? And there's another symbol for that. We can say that A is a strict subset of B if A is a subset of B, but they're not the same set, but it's not the whole set. They're not equal to each other. Right? It's very similar to the less than or equal to symbols, right? But it's a round shape instead of the sharp one. Okay, so let's do a more generally. So let's go back here. So for any integer, we can define we can define n times the integers as the set of multiples of n. So it's all the n times x such that x is an integer. So for example, 2 times the integers is, and this is what I was saying earlier, if we have a nice arithmetic progression, then we can write down our set like this. You can say this is minus 2, it's the even number 0, 2, and then for example 10 times the integers is minus 10, 0, 10, 20, like that. Right, so just the multiples of a certain number. So again, it seems fairly let's claim. It seems natural to see that in this case, the multiples of 10 should be a subset of the multiples of 2. But we want to practice doing that rigorously. So we want to show that if some element x is in the multiples of 10, then we want to show that it's also in the multiples of 2. So of course this means that x is equal to 10 times, let's say x prime for some x prime is an integer, but then x is 10 times x prime, but we can of course just write this as 2 times 5 times x prime, and then this. I mean, if x prime is an integer, then 5 times x prime is an integer, right? So then we're done. Right, so then we have that x is in the multiples of 2. And of course, it'd be pretty easy to show that the other way around isn't true, right? Because any of these, 2 is not going to be in the multiples of 10. Okay, so more generally, in this case, you should then see that there's something more general that we can say. If we have two integers, a and b, such that a divides b, then the multiples of b will be a subset of the multiples of a. So this was a proof. Right, and of course just following what we did before, but doing it more generally, we said that if x is in the multiples of b, then x is equal to some b times x prime for some x prime in the integers, but since a divides b, we have that b is equal to a times some, say, b prime for some integer b prime. I don't want to go too low, but I think I can still fit it here. So putting that together, have that x is b times x prime equals a b prime x prime, but b prime and x prime were both integers, so then x is in the multiples of a, and then we're done. Right. Okay, so that's how are we doing on time? Good. Okay, so let's go to the next one. So Remember that we wrote sets as, usually we write them as all the element x for which some proposition is true. So then how would we define the empty set, the set that has no elements in it, if we're using this definition? Right. We would need some.
Like a 0 with a cross slash.
Yeah, that's the notation. Yeah. So the notation is this. And we could define this as saying, I mean, one way that we write sets sometimes is by just listing all the elements. So we can just say it looks like this, right? But another way to define it, if we want to, we should be able to define it in this form. We can say it's all the elements x such that false, right? Because now for anything x, the statement false is going to be false, right? This is just a kind of a stupid proposition that's always false, right? So now we've defined the empty set because there's no x for which this is true, right? There's no x for which false is true, right? So that's just a rigorous way of defining the empty set. So the empty set is a little bit weird sometimes, and it's easy to make mistakes with it. Because if I make a statement about propositions about the empty set, propositions about, I should say, elements of the empty set, or I should be a little bit careful with what I mean by that, but they're always true, they're vacuously true. And what I mean by that is that I can say something like, all rhinos that live on the moon are green, and that's true, because for every rhino that lives on the moon, it's green, right? But that might seem like it contradicts all the rhinos that live on the moon are blue, but those are both true statements. Right, it's called vacuously true because there are no elements in the empty set. Right, so just from how we, and this is not just something that we agreed on. It kind of follows from how we define these things. Because if I say something like, how do we do this? If I say something like for all elements x in S, some proposition x is true. Then what do I mean by that? This is the same as saying for all elements, for all things, we have that for all elements either if x is in S, then p of x holds. And another way of saying this is that for all elements of x. So another way of saying if p1 then p2 is by saying we must either have that p2 is true or that p1 is false. So this is saying that either we have not, either x is not in S or p of x is true. There we go. Right, and once we get to this way of expressing this, we see that, of course, for the empty set, that's going to be true. Because for the empty set, this one's always true. So it doesn't even matter what's on the other side, right? Because this one's always satisfied, right? Because for any element, it won't be in the empty set. So then whatever else we want to be true doesn't matter. That's always true. And then, but if so this is for the sort of for all kind of statements, but if I make a there exists kind of statement, so we call those existential quantifiers, so propositions with existential quantifiers over the empty set are vacuously false. So an existential quantifier is something that says there exists, or there's at least one, or something like that, or for some, or something like that. Right? That's an existential quantifier. So then we compare this to saying, if I say there exists some x in S such that P of x holds, then what do I mean? Well, then I mean for all x. Not for all. There exists. Sorry. There exists an x in general, such that x is in S and P of x holds. Right, so this clearly breaks when we're talking about the empty set, because we're never going to be able to satisfy this side, but we have an and, so we have to satisfy it for the whole statement to be true. So then this is going to be always false for the empty set. So that's sometimes a little bit tricky when you think about the empty set, but just important to remember that anything that says there exists some element in the empty set is going to be false, and everything that says for all elements in the set is going to be true. Okay, so that's empty set. So we have until 11:40, right? Okay, good. Okay, so set operations. Let's put this next to each other. So, and you've probably seen these before, but we can talk about the union of two sets, A and B, and this is related to this other symbol. If I have two propositions, say P1 and P2, I can use this symbol, which means or, which maybe you've seen too, and you shouldn't confuse the two, because they're used in different situations. These are propositions, and those are sets. These are things that are either true or false, and these are sets that have elements in them. Right? They're different things, but they're related because we can, of course, say this. We can define as all of the elements x such that x is in A or x is in B. One of the two. Right? And similarly, the intersection of two sets is defined as all the elements such that x is in A and x is in B. And that is similar to the and symbol. And then we also have, what's the notation here? We also have set difference minus A, and this is sometimes written as B minus A. And that's all the elements in B that are not in A. So we remove everything from B that's not in A. And then finally, the complement. So the complement of a set A is all of the elements in U. And what is U? Well, U is some universal set that we're working in. But in order to define the complement, you have to say what the universal set is that your set is in. Right? And you have to be clear about that. You might be talking about the even numbers as being some subset of all the integers, or you might be talking about the even number as being a subset of the rationals, etc. But it has to be clear what the universe is in order to define what the complement is. Right? So it's all the elements in U that are not in A. Okay. Good. So in order, this is sometimes written as the complement superscript C. So this, you've probably done this where you draw Venn diagrams to just visualize what this means. And you may think that you know what a Venn diagram is, but do you really know what a Venn diagram is? So if I draw a Venn diagram with two sets, for example, it would look something like this. I would usually draw something that shows the universal set, and then I have my two sets A and B, and this is called a Venn diagram, right? This Venn diagram has two sets in it, and it has four regions, right? Because every element is either in the set or it's not in the set, right? So if there's two sets, that means that there's four total possibilities of being in a set or not in a set, right? You're in A, not in A, and you're also in B, not in B. So it's four total possibilities. So there's four regions: not in A, not in B, not in A, in B and A, and in A but not in B. Right? Those are the four options. Right? So if I have n sets and I draw a Venn diagram, then it would need to have 2 to the n regions. Right? So you have to somehow draw it so that every possibility of set membership exists in there. So with 2, that's pretty easy. But you often see things that people draw with 4 sets that they call a Venn diagram that isn't actually a Venn diagram. But that's just a sidetrack, because it's one of my pet peeves when people don't really understand what it's supposed to be. But anyway, for 2 sets, it's easy to draw a Venn diagram. So what was I going to do? All right, so the union of A and B is going to be everything. And what's important here to remember is that again, we define a set as something for which every element is either a member or not a member. Those are the two options, right? You can't be a member multiple times, right? An element can't be in a set more than once, right? It's either in there or it's not in there. So we don't have multiplicities. So if something is in the union, if something is both in A and in B, it's going to be in the union just once still, right? It's not going to be in the union 2 times because it's in A and in B, right? Just in there once. So then the intersection is going to be this region. Set difference. So we said B minus A, so it's going to be this side. And then for this one, we only need one set. And that's everything that's outside the set. So Venn diagrams are useful to visualize, but usually unless you're explicitly asked to draw a Venn diagram, it's not usually very strong justification for whatever you're trying to say. A Venn diagram is not usually a mathematical proof, right? I mean, it's possible, but it's not usually a very rigorous way of showing something, but it does really help you visualize things. So you should draw one if it helps you, but you should usually not give it as an answer to a question unless that is asked for, unless it says, draw the Venn diagram of this. So let's do some more practice. I think that clock is a little weird. So practice with these things. So example, so take some sets. 0, 1, 2. A and B are small sets, so we can just write out the elements. C is going to be a set with infinitely many elements, so it's going to be all the reals such that the value is at least 5. Such that the value is at least 5. So now, for example, as I was saying, if I take the union of A and B, then that's going to be 0, 1, 2, 3, 4, and 2 is not going to be in there twice because it's in both A and B. It's just in there once. It's no multiplicities. Sets only have unique elements. And then another example, A minus B would be all the elements in A that are not also in B, so we would exclude 2. Other examples, A intersection B. So here, this is another thing that you should be careful about. What's the intersection of A and B? Yes, it's the set that contains just 2. It's not the element 2, right? So this saying that this is 2 is wrong because this is a set. So we have to always remember to do the curly brackets around it because this object, the set that just contains 2, is not the same as the object that's 2, right? And that might, hopefully that seems like it makes sense, but it's very easy to make mistakes. It's a kind of mistake that's very common, and it's just kind of something you have to be very careful about when you're writing things down. So then, for example, if we take the union of B and C, then we get 2, 3, 4, and then all the real numbers that are at least 5, and there's not really an elegant way to write that down that's any more elegant than just basically the definition of the union, right? This would be all the elements x such that x is either, all the real numbers x such that either x is 2, 3, 4, or x is at least 5. But what I really wrote down there was just basically the definition of the union, right? There isn't really a more elegant way to write it, but that's okay. We don't have to have elegant ways to write down what a set is for it to be a set, right? But we could draw this on the number line. Say we include 2, 3, and 4. Those are just the points, and then everything above 5, starting at 5, would be included in that set, and that's fine. A set can contain a couple of integers, a couple of reals. It can contain different types of objects within a set. That's okay. Okay, good. How are we doing? Doing well. Okay. So let's do some slightly more difficult examples. So the example is to find the intersection of 2 multiples of 2 and multiples of 5. Okay, there we go. So if we so I guess your intuition or your claim, intuition would be that the intersection of the multiples of 2 and the multiples of 5 should be equal to all the multiples of 10, right? And how do we show that two sets are equal to each other? Well, you'd have to show that one is a subset of the other and the other is a subset of the first one, right? That's how we show that two sets are equal, because if that's both true, then we have that every element in the first set must also be in the second, but every element in the second must also be in the first, so then they're the same set. So we want to do 2 parts. Which one do we do first? So we want to show that the multiples of 10 are a subset of the intersections of the multiples of 2 and the multiples of 5. And we also want to show the other way around. Multiples of 2 and intersect the multiples of 5 are a subset of multiples of 10. That's the order that we'll do it in. My C's are getting worse and worse. Okay, so we'll start with that one first. Start by showing that multiples of 10 are a subset of multiples of 2 and the multiples of 5. And how do we do that? Just make this clear. It's around subset. So if let's actually start the other way around. I think the other way around is the slightly harder one, so we'll start this way around. Show that these are subset of the multiples of 10. So if x is in the set, then we know that that's because x is in the multiples of 2 and also x is in multiples of 5. So then this means that so x is equal to 2x prime for some integer x prime, and also x is equal to 5x a double prime for some integer. Getting tired, double prime. And now, what does this mean? Put this together, we have that 2x prime is equal to 5x double prime. And we know that x prime is an integer, so this means that 2 divides 5 times x prime. Right. So what does it mean for a number to divide some product of two numbers? Well, it could be that it divides either of those two numbers, or it could be that it factorizes such that one factor divides one and the other factor divides the other number. Right? It doesn't necessarily have to divide either of those two numbers in the product. Right? But 2 is prime. So it does, right? Because 2 can't be broken up into separate parts such that the separate parts can divide either 5 or x prime prime. Right, so since 2 is prime, we must have that either 2 divides 5 or 2 divides x prime prime. But of course 2 doesn't divide 5. So 2 does not divide 5, so therefore 2 divides x double prime. So now we're done almost, because this means that x double prime is equal to 2 times x, call this triple prime, for some integer x triple prime. And that's really the last step that we needed, because now we can say this gives us that x was equal to 5 times x double prime, which is equal to 5 times 2 times x double prime, which is triple prime, which is equal to 10 times x triple prime. And therefore x is in the set of multiples of 10. Right. That's the that's the conclusion where we wanted to get. But we have to be very careful here, right? Because, for example, if 2 wasn't a prime, then this wouldn't have been as easy, right? Then we weren't sure what divides what. So now we've proven this part. That's the proof that the intersection of these two sets is a subset of the multiples of 10. So now we want to go the other way around. So other way around is a little bit less annoying. I want to prove this part, so I don't really need the notes for this. So suppose that some y is in the multiples of 10, then y is 10 times some y prime for some integer y prime. And then we have that y is equal to 10 times y prime, which is equal to 2 times 5 times 5 times y prime, but of course that's an integer, so then conclude that y is subset of the multiples of 2, and we can do it the other way around. Y is 10 times y prime, which means that that's 5 times 2 y prime, which is of course also an integer, so then y is also in the multiples of 5. So that together means that y is in the intersection to intersect 5. And then we're done. Right? This proves that multiples of 10 is a subset of the intersection of the multiples of 5 and 2. Right, so then we have proven the subset relation both ways, so then the sets are equal. So now we know exactly that. Now we know exactly what this set is. Okay, so let's see. I think that clock's a little off. I think we have about 5 minutes left. Okay, so I don't know if we'll have time to finish this, but let's do, okay. Can at least make a start. So as another example, we can show that the intersection of the multiples of 10 and the multiples of 5 is just the multiples of 5. So how would we show that? Wait, this doesn't make sense. That's not true. I think he meant 10. Okay, that makes more sense. Yeah, so if we take the intersection of these two, then we just get the multiples of 10. So what's one way to show that an intersection between two sets is, and so if I want to say that, for example, the intersection of A and B is just A, is all of A. What what does that mean? That all of A is in B, right? If the intersection of two sets is just all of A, then A would be in B, right? So another way of saying this is just to say that this means that this is the same as saying A is a subset of B, right? And another way of saying that would be, for example, that if I take A minus B, I would get the empty set, for example. That's another way of saying the same thing, right? These are all different ways of saying the same thing. So if we wanted to prove this, those are all the different approaches that we could take, right? And also, one more thing maybe I should have said about the empty set is that the empty set is always a subset of any other set, right? The empty set is a subset of any set. So here we could either, probably the most obvious way to prove this would be to show that this is a subset of the multiples of 5, right? Which actually we already did, right? We did that earlier in the notes when we said that if for general A and B, we already said that for A, B, and C, and A divides B, we must have that B, the multiples of B, is a subset of the multiples of A, right? So we already showed that. So this one we could show very easily with what we already knew, right? And then we're done. So I think that's the end of the class. So if you have questions about anything that I said, I mean, I said mostly literally what Professor Dupree wrote down on his notes. But if you have questions about it, then feel free to email me for clarifications if anything was unclear about how I said something.